Yeah, so as Musharraf said, my name is Ankur. I'm a grad student in the AMP lab, and also a Spark committer and a maintainer of GraphX. So I'll be talking about supporting fine-grained updates to RDDs. And the motivation for this work was GraphX, actually, where we wanted to add vertices and edges to an existing graph. So we never actually ended up releasing that, but we did have this package that does that, and we think it's a broadly useful package, and that also brings together some interesting research ideas. So the background is that Spark allows users to build data sets, which are these parallel collections of records, and it lets people manipulate them using data parallel operators like map and reduce, or using SQL-like operators. And then Spark executes these transformations by breaking them up into tasks that run concurrently across the cluster. And the key thing is that each task executes independently on its input records and produces separate outputs. Now, Spark is meant to scale to large clusters where hardware failures or software bugs can happen in the middle of a query. So one of the key points of Spark and the predecessor systems like MapReduce was that they recover from failures by rerunning just the failed tasks without having to restart the whole query. So here, for example, if map task 2 fails, then it'll just be retried and everything else can go on as normal. So that avoids wasting resources on rerunning large queries. Also, some machines might have transient slowdowns from multi-tenancy or GC pauses. And so there's this feature called straggler mitigation, which can optionally launch speculative duplicate copies of slow tasks and then use the output of the task that finishes first. So here, for example, map task 2 is really slow, and then at some point it gets duplicated, and then the replica finishes faster. So both these features, the fault tolerance and straggler mitigation, require that each time a task is run, it leads to the same result, regardless of what else has happened in the cluster or on each machine. So that is this key property of task replayability. And Spark ensures that by requiring each task's input to be immutable, so RDDs are immutable, which is basically just done by copying the input before updating it, and also that tasks are deterministic. Now that's something that users just kind of have to do on their own, but it's partially guaranteed by making tasks single-threaded. So that eliminates a lot of concurrency, sort of non-determinism from interleaving. So immutability is the best way to ensure that Spark tasks are replayable. But people are also starting to use Spark for a widening range of applications. And a simple example is streaming aggregation, where we have a series of events, like one Twitter user following another, and we want to maintain some aggregate for each category. So something like a follower count here. Another example is just this broad class of incremental algorithms, where we have a stream of updates, things like new vertices and edges in the graph, and we want to do some incremental computation each time the graph changes. So Spark is a compelling platform for these applications because they often fit into a larger pipeline where the other operations are bulk transformations, like loading data or performing ad hoc queries or machine learning. But these applications don't fit into the bulk transformation model because they require these efficient fine-grained updates. So there are some obvious solutions that you just immediately think of, but they each have significant problems. One obvious solution is just to apply updates by modifying the data sets directly in memory or on disk. And that's fast, but comes at the cost of fault tolerance, because task failures will just corrupt the data by leaving different keys in different states. So here's an example where there's a task that does something simple like incrementing these two shared counters, x and y. And so if the task runs partially and then fails, then it can leave the state in this inconsistent state where you have x and y are different. And then even retries may just compound the failure. So a better option is to move data that has to be updated from an RDD into a transactional database that supports atomic batch writes. And in fact, Trident, which is sort of Storm system for getting exactly one semantics, does this directly. And also a research system called Naiad implements a similar system, its mechanism by using logging and checkpointing. But a common pattern in Spark is actually performing different computations on the same base data. So for example, extracting both the top ads and the most popular pages from the same clicks data set. So this kind of a thing where you want to reuse the same data and apply incremental updates to it in different ways is something that it's tricky to support. So in theory, databases that support multi-version concurrency control can do this, but they would need to take a consistent snapshot of the base data set before launching any task and preserve the snapshot for as long as the data set might be accessed. And this kind of a feature is pretty uncommon in databases and hard to support efficiently. Also, it complicates parallel recovery in the presence of mutable state, and that's one of the key features of Spark streaming. Yeah, so this is representing how long you have to keep a snapshot alive if you want to do updates in this way. So what Spark currently does is just to copy the entire RDD before updating it. And that makes sense when most or all the records are being changed, which is the common case. But for sparse updates, which are there in these applications that we want to support, that's very inefficient. So there seems to be this trade-off between immutability for fault tolerance on the one hand, and straggler mitigation on the other. For immutability for fault tolerance and straggler mitigation on the one hand, and supporting fine-grained updates on the other hand. So the question is it possible to get both? And it turns out it is. There's this class of data structures that supports both immutability and efficient updates. And these are called persistent data structures. Now this is named after the concept of persistence from the programming languages community, where persistent doesn't mean stable storage, it means that past versions stay around even after updates, kind of like Git. So here, persistent data structures support these efficient versioned updates that create a new version rather than modifying the existing one. And updates do that by returning a new copy that internally shares almost all of the structure of the existing copy. And that's easiest to do when the data is organized into a tree, because then updates only need to allocate a small fraction of new nodes. So you can kind of see that here we're modifying some leaf node and just copying a few nodes, and everything else remains the same. So we created this persistent index data structure in Java called part, and use that to implement a new kind of RDD called IndexedRDD. So IndexedRDD supports, it stores key value data, and in addition to supporting all the standard RDD operations, it can be efficiently updated without having to do a full copy. Also, it uses part to support some new fast operations, like really fast point lookups and pre-index joins. And it does all this efficiently, and you can see in reasonably little code. Okay, so here's how it works. RDDs normally store their contents in an array for each partition within like the block manager or the cache. And IndexedRDD just uses this special data structure, this part data structure, instead of just an array. And everything else remains the same. So keys are still partitioned using the standard hash or range partitioning. Updates are still stored in the lineage, which acts like sort of a write-ahead log for fault tolerance. And updates also return a new IndexedRDD that reflects them. So this whole thing builds completely on top of Spark, so it interoperates with batch computations. And then finally, here's what the interface looks like. So first, just from the signature up there, the extends, you can see that IndexedRDD will support all of the same operations as any pair RDD for any key and value type. But there is one restriction, which is this key serializer, which basically says that the key type has to be serializable. And we'll see how part uses this for indexing. Okay, but so now this supports things like get and multi-get, these things that aren't really efficiently supported on RDDs. It adds this functionality, and it does that by running tasks on the appropriate partitions and then just fetching the results out of this special data structure. Also, it supports updates, so put, multi-put, delete, again by modifying the appropriate partitions using the data structure and then returning a new IndexedRDD. And also, it's important to note, these work just like any other RDD operations in that they can only be called from the master. So you kind of have to go through the master to do updates. And the reason is that there's lineage that has to be maintained. And also, IndexedRDD re-implements the RDD, some RDD and pair RDD operations like filter and also a number of joins to take advantage of the indexing. Okay, so now let's just take a look at how this index data structure works. So the starting point is some work from databases called the adaptive Radix Tree. And this is a trie with a high branching factor. And, it's a trie with a high branching factor and with this feature called node compression. So this choice of branching factor of 256 is just a simplified tree operation. So that you just need to address each byte of key rather than shifting and masking. And then node compression is that to reduce space usage, nodes change representations based on their sparsity. So that's the number of non-null children. And then these representations are carefully chosen to keep the traversal speed high. So like I said, this is prior work, and that's just the starting point. But first, you might wonder, why are we picking this Radix tree? Why not like hash table or B tree, which is kind of which would be more common choices for indexing? So there are a few reasons. One is that unlike hash tables, Radix trees store keys in sorted order, so you can get fast range scans using in-order traversal. Second, compared to binary search trees or B trees, Radix trees have better asymptotic performance for long keys. And again, the reason is that they exploit the key structure, because each comparison in a binary search tree kind of only gives you back one bit of information, which is, is it less than or greater than the thing I'm comparing to. And whereas each comparison with the Radix tree can eliminate a lot of keys, like up to 255 out of 256 keys for each comparison. So there's this asymptotic difference. Also, there are these nice specialized operations, and this is actually the reason that we originally picked this data structure. It's that it supports these very efficient union and intersection operations. And again, it lets large numbers of keys be eliminated based on their prefix structure. And then finally, there's sort of this ideal of predictable performance, where there's no rehashing or rebalancing that has to go on. And so, in a sense, there's more predictability than the alternatives. Anyway, so now here's how we actually take this Radix tree data structure, this adaptive Radix tree, and get persistence, which is get efficient updates and immutability. So we use the tree structure to make sure that a single modification won't require a full copy, as I mentioned. And instead, when a node is modified, we just have to copy the node that is affected and make the modification, and then copy all the ancestors up to the root to reflect that pointer update. And then also, you might be worried about the tree height. Like if the trees are really deep, then you might end up with a lot of copying going on. But actually, well, first of all, the tree height is kind of logarithmic in the size of the information stored. And also, because of the high branching factor, it ends up being pretty small in practice. Okay, so we implemented this in C++ and Java, both. And I'll show some benchmarks of these things later. But also, in addition to path copying, each tree node maintains a reference count so that old versions can be removed while new versions still reference parts of the data. And that also helps us, that lets us do garbage collection in C++. And there's one kind of key optimization, which is that in some cases we can actually perform updates in place and avoid all this copying stuff. So in particular, updates to a version that will immediately be discarded can be made in place when they wouldn't affect anything else, any other versions. So here's kind of this figure that tries to illustrate this. So suppose that you have two versions of this part data structure, two different dictionary data structures, V1 and V2. And suppose we want to update V2 to create this new version V3. Then if V2 is never referenced after that, and if the update only applies to the nodes that are only referenced by V2 and not the V1 nodes, then that can actually just be done. It's equivalent to making the update in place in V2 and then just calling it V3. So anyway, so this is kind of the thing that gives this data structure a lot of its performance. Okay, so here the next thing I'm going to do is try and show that the performance and memory efficiency of this data structure are competitive with the standard mutable data structures, despite being immutable and giving this huge feature of versioning. So what we did was we compared this part data structure against some mutable things, a mutable hash table, mutable red black tree, and mutable B tree. And these are all C++ just for ease of benchmarking. So we loaded each data structure with sort of a sample, a benchmark set, and then made some random updates. And so here you can see that for small batch sizes, which is when you're frequently getting back a new version, then this data structure is kind of forced to do a lot of copying, and so its performance isn't quite as good as those mutable data structures. So hash table, for example, gets 800,000 of these operations, these updates per second, whereas in this case we only get about 100,000. But as the batch size grows larger and kind of the cost of having to create this new version gets amortized across more updates, then the performance of this part actually starts to exceed mutable data structures, even despite having this guarantee of versioning. So this is kind of a remarkable and nice thing. Okay. Also, these are just the kind of other useful benchmarks. So how fast are lookups, for example? Turns out they're pretty fast. They're competitive with hash tables. Scan performance also is pretty good. Not quite as good as a B tree, but and then memory usage again is comparable with these. Okay. Now, one thing was that to improve the scan performance, we were a bit concerned about this because scans are a really common operation in Spark. So if they're slow, it'll be bad. So we actually wrote this custom allocator that arranges nodes in the scan order when possible. And so that sort of does a slightly better job than the default C++ allocator and gives us this 3.6x improvement. Okay, so there's the first line is kind of the default allocator. Then we were able to get from 11 million elements scanned per second to 40 million. And then there's this optimal, which is factor of 4 or so more away. Okay, and also one other thing is that checkpointing is an important thing that Spark does often. So if you have this long lineage, then it ends up being important to checkpoint it every so often, so that you can kind of bound the amount of time that the Spark will take to recover in case of a failure. And so since this is also an important operation, we wanted to make this fast. So we kind of came up with this slightly interesting trick of incremental checkpointing. So the idea there is that we can sort of use a tree structure to track where the changes are happening, and if changes kind of don't touch some large part of the tree, then we can avoid having to rewrite that tree out to the checkpoint, compared to and instead just reference the previous checkpoint. And so this is some analysis for that. So the conclusion is basically that the blue line is representing a uniform write distribution. So if the updates are kind of happening all over the place with no pattern, that's the worst case for the scheme. But even then, if you update kind of fewer than 1 in 1,000 elements per partition, then this ends up giving a good 10x or more savings of checkpoint size. And then in the more realistic case, when updates are skewed, then it actually helps quite a lot, even for much more frequent updates. Okay, now finally, we kind of put this together in an end-to-end application. Here's a benchmark of it. So the idea was just to do streaming word count, where we're synthetically generating some words that we wanted to count, and then passing them through either Spark Streaming or Cassandra or our thing, or a kind of a upper bound, which is a C++ hash table that's mutable and has no fault tolerance. So that kind of provides weaker guarantees than anything else, but it serves to show what we could possibly do. So here you can see that it's log scale. So you can see that we're, first of all, outperforming Spark Streaming by a huge factor. And the reason there is that Spark Streaming, like I said, has to copy the entire in-memory state for each update, no matter how small the update is. So if only one word changed, or if only one word came in, and so we only want to increment one row in the word count table, then we'd still have to copy all million or 100 million of these word counts. So that's the reason for Spark Streaming's performance. And Cassandra does reasonably well. So, but it has to write data out to disk for one thing, and also it's not. Yeah, I mean, let's just suffice to say that even despite batching and other optimizations, it ends up having to have some unavoidable overhead that makes it not quite as fast. But then the real thing is that we're actually able to get within sort of 18% or so of the this upper bound of the hash table. So that was also pretty, we were happy with that. Okay, so finally, this thing isn't perfect, so there are a few limitations. One of them is that in the Java version, which is what is actually available for Spark, for very large data sets, you can encounter GC pauses, which will hurt predictability. So there's this idea, which is that we already maintain reference counts for each node for our internal use, and so we actually could use these to do garbage collection off heap. and also could use object pools to control memory fragmentation if we did this. So that kind of ties into Project Tungsten, which is to move more things in Spark off heap. And secondly, in cases where there are long keys that have high skew, that could actually artificially increase the tree depth. And I can go into this in detail maybe if you're interested. But in this very special case, there are other alternatives that would be better, like a copy on write B tree. Okay, so it's kind of the one high-level takeaway that I think this research came out with is that efficient updates to immutable data isn't a contradiction. You can actually have both. But also, this is a Spark package, and you actually can use it. So there's this exercise after lunch that will let you try it out. Okay, so I'm happy to take questions now. Okay, so the first question was, does this inherit from any existing Spark component? And so the answer is, currently it just sort of depends on the Spark core because it extends RDDs. So there's a number of other packages that do that similarly. But it'd be nice, we're interested in having this work for Spark SQL. So to work as an index that you can just turn on for a data frame and then let you, make updates to the data frame. So that would, in that case, be for Spark SQL. The second question was, was whether we've considered using this for aggregation in case of like if you're doing OLAP. So if you're scanning some big data set and then on the fly computing some aggregate, then so the answer to that is, so in that case, I think versioning wouldn't be as useful because like you probably don't care what the aggregate was for some partial subset of the data. And in that case, Spark actually already has like the shuffle component, which kind of ends up doing a similar thing internally. And so for these kinds of internal use cases, it's probably more efficient to use the conventional mutable data structures. But where part comes in is when the user actually has to get back some version data, and then kind of wants to be able to have access both to an old version for maybe reasons of applications or because of the application or because of fault tolerance, and also to the new updated version.
Any other questions? Yeah, so I mean, we can, I guess, again, thank the speaker and then move on.